Good morning, sir.
Good morning, sir.
So today is the um, today is the 10th session. We'll listen from Dr. Vijay Kumar Bulasra. He is the head of the MN and IT department, not chemical engineering, MN and IT. 1 minute, sir. I have to check. Okay, fine. Uh, His qualification is a PhD in chemical engineering. Previously worked as a different institute, namely Thapar Institute of Engineering and Technology, Patiala, 7 years. CB Raman College of Engineering, Bhubaneswar, three semester, and NIT Andhra Pradesh, 1 semester. Prior to joining at MA, NIT guided to PhD thesis and 9 MTech thesis at TIET Patiala, published 33 SCI journal articles, 3 Scopus papers, and 3 other international journal papers. The Scopus index, H index is 16. Also had 4 conferences, presentation abroad, and 26 conferences, presentation in India, serving as external examiner for PhD thesis, editorial board member for 4 international journal, and reviewer of several high-impact SCI journals. So now, sir, over to you, sir.
Thank you very much for a nice introduction. So I'm sharing my slide. So I hope the screen is visible.
Yes, sir. Yes, sir. Visible.
Okay. Thank you. So welcome to the ATAL Online FDP at CV Raman Global University, Bhubaneswar. So Rudra sir has already told about myself, as I am working at MNIT Bhopal. And I actually belong to the state of Andhra Pradesh, and I did my schooling and up to BTech from Andhra Pradesh, then did MTech and PhD from IIT Guwahati. Then I worked as an assistant professor at Thapar University, Patiala. I have good experience at CV Raman College of Engineering, Bhubaneswar. So then I had a short tenure at NIT Andhra Pradesh also. Okay, so sir has explained all the things about my profile, and I'm working on membrane separation processes, adsorption process for wastewater treatment. Mostly membrane and adsorption both are related to wastewater treatment. Then I have also interest in working in the catalysis, synthesis of different catalysts, and studying of reaction kinetics. Okay, so I also worked on the preparation and synthesis of zeolites. They are used in adsorption process for removal of pollutants. Okay, and Today's topic of my presentation is utilization of waste fly ash for fabricating membranes, and membranes are used for wastewater treatment. Okay, so this waste fly ash, previously the fly ash generated from the combustion of solid fuels like coal-fired thermal power plants. So a huge amount of fly ash is generated in coal-fired thermal power plants, and it was previously discarded as waste, but it found some applications uh, in the preparation of cement, okay, bricks. So those are some low value applications of fly ash. However, if we can use fly ash for for development of value added products like membranes, then its value increases, and the pollution problems arising from the disposal of fly ash also reduces. Okay, so this fly ash we try to use this make use of the fly ash for making ceramic membranes, and those membranes are used in wastewater treatment. Okay, so in this study, this wastewater, we studied synthetic wastewater solution using or employing a single pollutant or single solute. So coming to the topic, most of you are familiar with the term membrane. It is originated from a Latin word membrana, and it means skin. Okay, so this membrane is a thin barrier placed between two phases. Two phases means one is the wastewater stream, or you can say it is the solution containing the solute and solvent. Okay, and other phase is a pure solvent. So we want to separate the solutes from the solution, and we want to obtain pure solvent or pure water with respect to the wastewater treatment. So this membrane acts as a thin barrier placed between two phases, and it membrane allows one or more constituents selectively to pass from one medium to the other in the presence of a driving force. So in the pressure driven membrane processes, the pressure difference is the driving force. So when we apply pressure on the solute side, so the solvent is forced to flow through the membrane and under the driving force of the pressure difference. It is also called transmembrane pressure or pressure difference. Okay, so there are other processes which work on the difference in concentration as the driving force, but in wastewater treatment we focus mainly on the pressure driven membrane processes. Okay, so here this membrane in most of our pressure driven membrane processes, the membrane will be having the fine pores or openings through which the solvent can pass through. Okay, so in case of semi-permeable membranes like those used in the reverse osmosis, the membrane allows only solvent to pass through, whereas in other processes like microfiltration, this ultrafiltration and nanofiltration, there will be a finite size pores and which allow one or more constituents to pass through the membrane. Okay, so this is about membrane filtration, and again this filtration can be operated in two different modes like dead end filtration and cross flow filtration. So in the main difference is that in the dead end filtration, like if this is the membrane and solution solution containing solvent and solutes will be placed on one side of the membrane and pressure is applied so that the solvent passes through the membrane. So this is called dead end filtration or direct filtration, and in another mode of filtration we use the solution will be on one side but it is flowing parallel to the surface. Okay, so we'll get the permeate. This is called permeate, or that is the pure water which is coming out of the membrane is called permeate. So here what is here there are only two streams. One is feed stream and other is the permeate. Okay, but in this case there are three streams, that is feed stream containing, let's say you have 100 ppm of the impurities, and permeate is containing less than 1 ppm after suppression by the membrane. And same way here also we are using same feed 100 ppm and we are getting a permeate of less than 1 ppm kind of pollutants. Okay, but there is another stream called the rejected stream that contains a high amount of the pollutants, okay, greater than 1000 ppm. So this is the retentate or reject stream. Okay, so the main advantage of this this is called cross flow filtration. So main advantage of this cross flow filtration is that the fouling is minimized, and in case of this dead end, that is first case, there is a issue of severe fouling. Okay, because when we are feeding, means giving a solution feed containing 100 ppm of the solutes, only the solvent is coming out of the membrane and all the solutes are accumulating near the surface of the membrane. So when solutes accumulate, that is the phenomenon is known as concentration polarization. So this concentration polarization, due to this fact, the concentration of the impurities will be very high near the membrane surface. So here more and more solutes will be accumulating and they cause blockage to the pores of the membranes. Okay, so they block some of the pores of the membranes and hence the permeate flow rate will be reduced. Okay, because the flow or permeate flux is it depends on the porosity of the membrane. So when there are more number of pores, if all pores are open, then we'll get the maximum permeate flux or permeate flow rate. But when some of the pores are blocked by these the solute particles, then we get a decline in the flow rate of the permeate. Okay, so that issue is most commonly observed in case of the dead end filtration, whereas in case of cross flow filtration, the particles which are accumulating, because only solvent ideally solvent is flowing to the membrane and solutes are rejected by the membrane on the feed side. Okay, but feed, this solution is flowing tangentially, or this is over the surface, and here we are collecting retentate or rejected stream. Okay, so this flow over the surface, it sweeps away the particles accumulating or the solutes accumulating near the membrane surface. So there is the problem of the membrane fouling or this concentration polarization is reduced in the case of cross flow filtration. Okay, so for theoretical studies or for laboratory characterization of membranes, for small scale applications, dead end filtration is easy to employ. So maybe in the laboratory scale we will be employing dead end filtration, but on industrial scale or on a large scale we will be using the cross flow filtration. Okay, so even the in the filters that we use for domestic RO, that is reverse osmosis RO systems, they contain a series of membrane processes. So those are all in a tubular shape. Okay, so in the tube inside, the feed flows inside the tube, and this tubular membrane will be having the pores, and pure water will come out of the membrane, and on the other side will collect the retentate. So one side feed, other side retentate. Okay, so there will be a covering for this membrane which collect the purified water. So we'll get purified water, that is permeate, and retentate from the other side of the membrane. That means here also in the commercial and domestic filtration units, the flow employed is cross flow. Okay, that is why we are able to use these membranes for about 1 year, then after a year or after, if depending on the usage, if it is used continuously, then maybe within 6 months we need to replace the membranes, or if we continue use occasionally, then the membranes it will work as long as 1 year, even more than 1 year. So this cross flow filtration is advantageous over the dead end filtration. Now, as we've seen in the previous example, that in domestic filters also we use the membranes for purifying the water. Not only for the purification of water for drinking purposes, but there are many applications in the industry. That means the membranes can be used in industries, chemical industries, for various applications like product separation and purification, as in certain reactions, if more than one product is formed, they can be separated, or in case if a solid product is produced and it is to be separated from the solution. So membranes are used for separation and purification of the products produced in the chemical industry. Also in catalysis, if sometimes if catalyst is used in powdered form, then these catalyst particles may be carried away by the fluid streams during the reaction. So these catalyst particles will be recovered with the help of membranes. Okay, so some membranes are used to recover these catalyst particles from the reactor, reaction that feed streams. Otherwise, these particles, if they are sometimes nanoparticles are used for high surface area, to obtain high surface area, and nanoparticles, particle size, when you reduce the particle size, the surface area will increase and it will be its activity also will increase. So therefore these catalysts sometimes are used in powdered form, and to recover the powdered catalyst particles we can use membranes. Okay. Similarly, in wastewater treatment, this membrane separation is also part of the advanced separation process. Like in primary treatment, after the primary treatment, then that is separation of suspended solids and large particles. We'll go for secondary treatment, that is biological treatment. Then after that, this advanced treatment is used as a tertiary treatment process, in which membranes are also find applications. Okay, so in the advanced treatment, like certain heavy metals, they cannot be reduced, they cannot be removed in primary or secondary treatment. So to remove these heavy metals, the people use different methods like adsorption, membrane separation. So these all come under the advanced treatment processes. So in the advanced treatment process, membranes also find an important role. Okay. Similarly, a membrane separation. This membrane separation, it processes. There are different membrane separation processes. They differ based on separation mechanism, that is driving force. As we talked about the pressure-driven membrane process, which are most common in wastewater treatment. Similarly, the driving force can be concentration difference, or it can be the electrical potential difference. So and the separation process also differs based on size of the separated particles or solutes. Okay, so if we know the average size or approximate size range of the particles or solutes to be separated, then we can choose the proper membrane separation process. Okay, for example, if the water contains bacteria or paint pigments or any organic matter like humic substances, humic acids, then we will go for microfiltration. Okay, so these four processes are widely used membrane process in a wastewater treatment. So if the wastewater contains these impurities like bacteria, if you want to separate bacteria from wastewater, or paint pigments from the water, or any natural organic matter like humic acids. Okay. Also, the oil water emulsions can be separated using microfiltration process. Even some fruit juices are also clarified using microfiltration membranes. Okay. So the main difference among these processes is the membrane pore size and the pressure used. Pressure is, this is the driving force for this separation or for flow through the membranes, and this pore size, it will uh, dictate the type of solutes or type of particles, substances that can be separated or rejected by the membrane. Okay, so in microfiltration, the pore size of the membrane, it ranges from 0.1 to 10 micrometers. Okay, so in this is the pore size range for microfiltration. However, most of the microfiltration membrane-based filtrations for industrial applications and wastewater treatment, they prefer submicron range pores. Okay, so submicron means it is pore size is less than 1 micrometer. Okay, so submicron range pores or submicron range membrane is highly preferred for microfiltration applications. Okay, so these are suitable for removing of bacteria, paint pigments, and organic matters. Oil water emulsions can also be treated. Similarly, the next process is ultrafiltration process. This is also widely used to membrane process. So here it is slightly superior to the microfiltration membranes, in which the pore size ranges between 2 to 100 nanometer. So this 100 nanometer means it is 0.1 micrometers. So the pore size is smaller than that used in the microfiltration. Okay, so pores are small means the if so pore openings are small, then flow rate or permeate flux or permeability also reduces. Therefore, the flow rate through the membrane is becomes reduced, and to increase the flow rate, so to meet the required demand or required load, because like 1,000 liters per day of or per hour of wastewater is produced, we want to treat this much of water per hour, 1,000 liters per hour. Then if we use microfiltration membrane, then because its pore size is relatively large, so it will allow this much of the flow rate through it. However, when you use ultrafiltration membrane, its pore size is small, so we need to increase the area of the membrane. That is, membrane area needs to be increased, and also the pressure also higher. Okay, if you use low pressures, then you will get very low flow rate or low flux. So we need to increase the pressure so that the permeate, sufficient quantity of permeate, considerable amount of permeate is obtained per unit time. Okay, so the pressure required, the pressure difference or transmembrane pressure required in the ultrafiltration process is higher, that is 1 to 10 bar. Generally, people use around 5 bar or 5 to 6 bar is most commonly used to pressure. However, the range, it ranges from 1 to 10 bar. So the pressure required in the ultrafiltration process is higher. So higher pressure is required. However, its pore size is small, so we can separate. In separation is superior to microfiltration membrane. That means this ultrafiltration membrane, it can separate all those which are separated by microfiltration process, and in addition to this bacteria, paint, or organic matter, oil water emulsions, or fruit juice clarification. Additionally, viruses can be separated, and proteins can be separated, that is from like dairy wastewater or some wastewater content, food processing industries, wastewater arising from food processing industries also contain different proteins. They can be separated in ultrafiltration process. In micelle, these are surfactants. So surfactant micelles also can be separated using ultrafiltration membranes. Okay. So ultrafiltration membrane is superior to microfiltration membrane in terms of the pore size, which is smaller. Smaller pore size is desirable. However, one main drawback is the high pressure. Okay. So these first two processes, microfiltration and ultrafiltration, these two processes are economical compared to nanofiltration and reverse osmosis. Because in nanofiltration, although the pore size is very small, that is 1 to 2 nanometers only, but the pressure required to get the sufficient amount of flux through the membrane is 3 to 20 bar. So as the pore size decreases, the pressure required to, that is pressure means the driving force required will be higher. So in nanofiltration case, the driving force is 3 to 20 bar. That means more than 10 bar is generally required for operating nanofiltration membrane. So this nanofiltration process can separate dyes, sugars, multivalent ions. Okay, so this nanofiltration process finds important application in textile industries, because the textile industries contain especially the dyeing operation or dyeing process uses dyes plus some salts in water. Okay, so these salts they can be these sodium sulfate or sodium chloride. Okay, so this solution can be separated by nanofiltration process, because nanofiltration membrane can separate, or it will reject dyes, because nanofiltration process can remove dyes, reject dyes. So what remains is the salt. So salt solution, salt plus solvent, that is water, will come out after nanofiltration membrane. So we don't need to again separate this salt from water, because this salt plus water, this can be recycled in the textile industry, because wherever salt is used, this salt water can be recycled there. If required, then we can separate salt from water using reverse osmosis process. Okay, so this dyes, if it is a single dye is water is separated, then this dye also can be recovered and reused. Well, okay, so but this wastewater from textile industry will also contain certain other impurities like cotton fibers from the this cloth. So these fibers will be removed by pre-treatment. Okay, so pre-treatment process can also include the microfiltration. Like in our RO unit, there is a filter called pre-filter. So this pre-filter pore size, sometimes it will be 10 microns, sometimes it can be 2 microns. So depending on the impurity that is to be removed, we select the type of pre-filter. So pre-treatment is used to remove the fibers and other suspended solids or other impurities from these wastewater or containing dye stuff. Then this dyes, the solution containing dyes and salts is separated with the help of nanofiltration membrane. Okay, so this not only dyes, this sugars dissolved in water, they can be separated using nanofiltration, and multivalent ions can also be separated by nanofiltration membrane. Reverse osmosis membrane can separate everything except the solvent, which is water in the wastewater treatment, because in reverse osmosis process, the membrane used is also called semi-permeable membrane. Okay, so it is permeable semi-permeable. It allows only solvent to pass through the membrane. That means only water will pass through and all others will be rejected by the membrane or retained over the membrane. So all monovalent ions can be separated by reverse osmosis process. So the pore size is less than 1 nanometer and pressure required is as high as 80 bar. Okay, that means very high amount of pressure is required. More so commonly greater than 20 bar is required for operating reverse osmosis membranes. Okay, so these are expensive process because they require nanofiltration. Reverse osmosis membranes are expensive due to their very small pore size, and also the operating cost is very high for nanofiltration and reverse osmosis process, because we need to employ very high pressure differences so that the required amount of pure water is obtained per unit time. That means to treat large volumes of effluent at a given time, we need to use large number of nanofiltration membranes are increased surface area, and the pressure required also will be very high. So these two processes, nanofiltration and reverse osmosis, are expensive, and the microfiltration and ultrafiltration process are economical. Therefore, in real wastewater which contains a different or a number of impurities which fall under different categories with different sizes, we have to use a series of all these processes, that is microfiltration, then ultrafiltration, then nanofiltration, finally reverse osmosis. Okay, so all these processes are employed in series to remove all impurities from the wastewater. If we use reverse osmosis membrane alone, it also removes all impurities, but the problem is the fouling. So these pores are very small in size and pressure required is very high. So when we apply this much of high pressure, most of the impurities which are large in size, that like bacteria, viruses, paint, pigments, okay, dyes, they will block the pores of the reverse osmosis membrane. So to reduce the load on RO membrane, we'll use pre-treatment stages. That means this microfiltration, ultrafiltration serve as pre-treatment processes. Okay, so in this pre-treatment process, most of the other impurities can be removed and load on NF or RO membranes will be reduced. Okay, so in this way, we will use the membrane separation process. So in household RO or in any commercial RO unit, it contains series of membranes. So these membranes include microfiltration, ultrafiltration, so either nano or reverse osmosis. Okay, so reverse both the pore size range is very similar, like less than 1 nanometer or 1 to 2 nanometers. So one of these two is used, then microfiltration and ultrafiltration process are used as pre-treatment steps. Okay, because these are less expensive. The membrane, we can replace microfiltration membrane or ultrafiltration membrane at a low cost, whereas this nanofiltration and reverse osmosis membranes are expensive to replace periodically. Okay, so therefore, in case of there any issues with the purity of the water or the amount of water that is separated, that is the load, then we can replace the microfiltration membrane or ultrafiltration membranes. Okay, so that because the most of the impurities will be separated in microfiltration and ultrafiltration processes. So if these are fouled, if the membrane fouling occurs in the initial stages, then we have to replace these membranes, microfiltration or ultrafiltration membranes, because these are less expensive. If we do not use microfiltration, ultrafiltration pre-treatment, then we need to replace nanofiltration NF and RO membranes periodically. Okay, so which are expensive. So to reduce the load on these final treatment steps or final treatment process, we will employ pre-treatment stages or treatment process. Okay, so in the same is explained here, like relative size of common materials, like it here it is 100 micrometers and here it is 1 nanometer. Okay, so between these, like microfiltration process, it ranges from like 0.1 to 1 micron or 1 to 10 microns. So this range is for microfiltration process, and in this range of pore size, the solutes that can be separated include these paints, okay, that we already discussed. The bacteria also can be separated. So whatever is named to the right of this will be easily separated. So to the left of this microfiltration process, we will have smaller size, because here the scale is within the size increasing from left to the right. So right sides we have larger particles and left side we have smaller particles. So larger particles can be rejected or separated by the membrane. The microfiltration process can separate paint pigments, bacteria, yeast cells. Okay, and prior to microfiltration, like we can also go for particle filtration. Okay, so particle filtration includes the sand filters or any cloth filters which can separate some bacteria of larger size and yeast cells. Okay, and ultrafiltration covers the pore size range here, even here, that is up to 0.1 micron means 100 nanometers. So 2 to 100 nanometers is the ultrafiltration range, and 1 to 2 nanometers is the nanofiltration range, and less than 1 nanometer is for reverse osmosis pore size range. Okay, so sometimes the membranes are not characterized in terms of its mean pore size, and sometimes in terms of the molecular weight cutoff given in Daltons. Okay, so 20,000 Dalton means it is 20 kilodalton. Okay, so molecular weight cutoff is also determined experimentally for any given membrane. So characteristic membrane can be characterized in terms of pore size, which requires sophisticated techniques to determine the pore size distribution of the membrane, and it can be characterized in terms of the molecular weight cutoff of the membrane. So depending on the molecular weight cutoff of the membrane, we can use the membrane for different applications. So here also another diagram showing the membrane separation process, like in a microfiltration process can remove larger particles. Then the particles which pass through microfiltration membranes, they can be the pure water or solvent, then monovalent ions, multivalent ions, then these polymers and proteins, viruses. Okay, so microfiltration can separate the particles and bacteria cells. Then ultrafiltration process can separate the polymers, proteins and viruses, whereas nanofiltration membrane can separate small molecules such as dyes and multivalent ions and salts, whereas reverse osmosis can separate everything except the solvent, because we are using semi-permeable membrane which allows only the water or solvent to pass through it. Okay, so these are used in a series. These processes are used in series to remove various types of impurities present in the real wastewater. Real wastewater will contain a number of impurities which will be separated, which require different processes for its separation. Okay, which range the impurities or solutes may differ in the size and properties, so that if these processes are employed in series, then we can be able to separate all these processes, all these impurities or pollutants. Okay, so now when we come to the classification of membranes, they are generally based on the material. They are classified as polymeric membranes and so uh, these two are the commonly used membrane materials, polymer membranes and ceramic membranes. So mainly in our households we use polymeric membranes, have certain advantages, like they are relatively low cost compared to the ceramic membranes, because ceramic membranes are expensive because they require high. So there is some network issue at my end, so I'm just reconnected. Right. So when we talk about the material of this is membrane, based on the material, the membranes are categorized into two major types, that is polymeric membranes and ceramic membranes. Okay, so polymeric membranes, they are relatively less expensive as compared to the ceramic membranes, because the ceramic membranes require high temperature sintering. Sintering or thermal treatment. So it requires high temperature sintering. So the operating cost for that operating cost means in the preparation, the cost is high, as well as the material cost, the raw material cost is also very high. So ceramic membranes are expensive because of raw materials used, which are expensive. That is alumina, zirconia, titania. These materials which are used for fabricating ceramic membranes are expensive. They also require high temperature sintering. Therefore, these ceramic membranes are expensive as compared to polymeric membranes. Therefore, in most of the membrane process and for drinking water purification, polymeric membranes are used. But polymeric membranes have certain disadvantages also. The advantages include low cost, small and uniform pore size, and ease of fabrication. These are the advantages. Whereas poor mechanical strength, that means if you want to use or remove monovalent ions, you have to apply very high pressure. That is, in reverse osmosis process, we need to use around 50 megapascals or 50 bar, sorry, 5 megapascals or 50 bar. So at this very high pressure, the polymeric membranes cannot withstand this much of high pressure, and they require using of ceramic membranes. Also, poor chemical resistance. If you are using highly acidic or corrosive solutions, then these polymeric membranes are susceptible to damage. And poor thermal stability. So these polymeric membranes cannot be used to separate the solutions at a very high temperature. Okay, so like in chemical reactors, the reactions are carried out at very high temperatures like 400 degrees centigrade. So at these product cannot be separated or filtered using the polymeric membranes, because polymeric membranes have poor thermal stability. So the pores may be deformed, and pore size may be different, and the membrane itself may get deformed or distorted. Okay, so when the membrane gets deformed, then its efficiency or separation efficiency becomes will be affected. Therefore, we will avoid these polymeric membranes when dealing with high temperature streams or the corrosive streams. Okay, so for that purpose, we use ceramic membranes because they have various advantages. Like as in the case of the highly acidic or basic solutions, the ceramic membranes show good chemical stability. Okay, so they are suitable for even like in the textile industry, effluents will be having high pH basic, and some other processes like tanning industries or other processes will be acidic in nature. So in those cases, these are very effective, are very useful. The ceramic membranes are very useful. They withstand high temperatures. Okay, so this is, as we said, whatever is the drawback of polymeric membranes is the advantage of ceramic membranes. They withstand high temperatures, they withstand high pressures, especially reverse osmosis, nanofiltration. Those processes they are operated at high pressures. So these therefore they require uh, to have high mechanical strength. So these ceramic membranes will have high mechanical strength, so they withstand high pressures. Okay, they are durable. They have longer life as compared to polymeric membranes upon continuous usage, and they can be regenerated. Regenerate means after using it, they can be cleaned and regenerated, and they can be reused. So there are certain disadvantages. Most important disadvantage drawback is the major drawback is the cost. Cost is the major drawback for ceramic membranes. It has also non-uniform pore size. The pore size distribution is there will be a wide distribution of pore size. Like suppose if we want to have 50 nanometer pores, okay, or 100 nanometer pores, but there can be pores of 500 nanometers also on the membrane. Average pore size may be 100 nanometers, but there is a wide distribution of pore sizes. So non-uniform pore size is also one disadvantage for ceramic membranes. Okay, in case of polymeric membranes, they are easy to fabricate, and also they will have uniform pore sizes. That means all pores have similar size or same size. Whereas in case of ceramic membranes, different pores will have different sizes, that is diameters, and then hence it is one of the disadvantages of the ceramic membranes. Okay, but still we try to make the uniformity that in pore size with means by altering the operating conditions. That means the heating rate in the sintering process. Heating rate is one of the controlling factors for pore size distribution. Okay, also low porosity as compared to polymeric membranes. Here most of ceramic membranes porosity is less than 50% for all ceramic membranes, and commonly the porosity is even less than 40% for ceramic membrane. Whereas in polymeric membranes, the porosity can be very high, greater than 60% for polymeric membranes. Okay, so more than 60% porosity is very common in case of polymeric membranes, whereas less than 40% porosity is common for ceramic membranes. Okay, so porosity is one required property, that is, it should have, as the number of pores increases, then porosity is the fraction of pore volume. That is total volume of pores divided by the volume of the membrane, total volume of the membrane. So the fractional volume that is occupied by the pores is an important property of the membranes. So porosity should be as high as possible, and there should be uniformity in pore size. And another disadvantage, it is a very minor disadvantage, is that heavier than polymeric membranes. These ceramic membranes are heavier. That means in case if you use polymeric membranes in the RO unit, it is lightweight, and if you use ceramic membranes in the water filter, it is heavy in weight. Okay, but it is not a major drawback, it is a minor drawback. So mainly these ceramic membranes are used in separation of oil water emulsions, then removal of bacteria and heavy metals and dyes from wastewater. Okay, so these oil water emulsions arise from the wastewater generated by these oil refineries, oil wells. Okay, so that wastewater will contain oil water emulsions. If the oil concentration is more than 1000 ppm or mg per liter, then that can be easily separated by this simple gravity techniques, like gravity techniques. Then due to the difference in the density, the oil can be separated. But if the oil concentration is less than 250 ppm, then the droplet size is very small and it forms stable emulsions. Okay, so these stable emulsions cannot be separated easily by gravity methods. Okay, so these require the membrane separation for separating a treatment of stable oil water emulsions. Okay, similarly, removal of bacteria, heavy metals, dyes, they also employ ceramic membranes. So ceramic membranes are used for removal of bacteria, removal of heavy metals, and also dyes. There are various other methods which have certain advantages and disadvantages, but as far as the ceramic membranes are concerned, these are the major uses in wastewater treatment, that is separation of oil water emulsion and removal of bacteria, heavy metals, and dyes. So these ceramic membranes will come in different configurations. Like here, this one is these two, that is, these are rectangular and circular disc type. They are flat membranes, and these are tubular. Okay, so tubular membranes are useful in the cross flow filtration, and they are employed in domestic filters, whereas in industries the flat membranes are preferred over these tubular membranes, because these flat membranes are easy to clean. Okay, whereas if internal surface of the tubular membranes are fouled, then cleaning becomes difficult, whereas in case of flat membranes, the cleaning is easy. So they are easy to clean, therefore they are preferred in the industrial applications, especially which means the wastewater, if it is if it contains fouling agents, then it requires the periodic cleaning of the membranes. Okay, so flat membranes are used there also, and in laboratory, if we are synthesizing the membranes, it is easy to make prepare flat membranes as compared to tubular membranes. In case of tubular membranes, we require some different equipments like extruders. Okay, so using extruders, we can prepare tubular membranes, but the success rate is less. For in case of ceramic membranes, the success rate is less in making the tubular membranes. They may be defective. So flat membranes can be easily prepared using a simple die. Okay, so using a simple die, we can fabricate flat type membranes. So now coming to the preparation, the main drawback is the cost of the ceramic membranes. So to overcome the cost, there are two options, like to change the raw materials which are highly expensive. Another is to reduce the sintering temperature that is required for making of ceramic membranes. Okay, so previously the ceramic membranes are prepared using alumina, zirconia, which are highly expensive. Okay, so alumina, zirconia, titania are highly expensive raw materials. That is, raw material cost is high and they require high sintering temperatures. That is more than 1300 degrees centigrade. That is up to 1500 degrees centigrade temperature is required for sintering of these materials, raw materials. Okay. Also, cost of ceramic membranes, it can be reduced by using some low-cost raw materials such as the kaolin. Kaolin is a low-cost clay mineral. Its cost is only 5% of the cost of alumina or zirconia. Okay, therefore, kaolin is widely used for preparing ceramic membranes, especially in the on laboratory scale for microfiltration process. Okay, because one major issue with kaolin based membranes is we cannot prepare nanofiltration or reverse osmosis membranes. The pore size is in micrometer size. Okay, the pores are in micron size. We cannot get nanometer size pores with using kaolin itself. Okay, but the cost of membrane will reduce, and depending on the pore size of the prepared membrane, we can apply it in suitable processes. Like if the membrane pore size ranges between 0.1 to 1 micron or 1 to 10 micron, 0.1 to 10 microns, then they can be used for microfiltration. Okay. So this kaolin is a low-cost alternative raw material for preparing ceramic membranes. And some efforts have been made to reduce the cost of raw material further by using no-cost raw materials such as fly ash. As we discussed in the beginning, that fly ash is a waste generated by combustion of solid fuels, especially in the coal-fired thermal power plants. It is produced in huge amounts, and it finds some applications like in the preparation of cements or in the preparation of bricks. Okay. However, if we can utilize this fly ash for value-added products like membranes, then its disposal issues will be reduced. So, however, these fly ash based membranes, we have prepared fly ash membranes with fly ash alone with certain additives, but they have large pore size that is greater than 2 microns. That means the applications are limited. When the pore size is greater than 2 microns, means it is the average pore size. That means it has pores of 5 micron also. Some pores will be like 0.1 micron or 0.5 microns. Okay. There is a distribution of pores in the membrane. So average pore size is about 2 2 microns when we use fly ash as the raw material for making membranes. And they also had lower strength, that is less than 20 megapascals. So generally it will be preferable to have a high mechanical strength, because that is the one major advantage of ceramic membranes. Okay, so we should not compromise upon the mechanical strength of the ceramic membranes. So in that case, the kaolin based membranes are superior with respect to the mechanical strength of the membranes. We in this particular work, we tried to use the mixture of fly ash and kaolin, because this drawback is that fly ash membranes have large pores and lower strength, okay, compared to kaolin. And kaolin based membranes have relatively smaller pores and higher strength. Therefore, we investigated on the low cost membranes with high strength by changing the raw materials, that is mixing of different raw materials. So we mixed 2 raw materials, that is kaolin and fly ash. Okay. We can also study changing the additives, that is a different work we did. So for preparing the ceramic membrane, generally lab scale on lab scale, 2 methods are commonly used. One is the paste casting method, that is this is easy to apply, but it is subject to manual errors. Whereas there is another method, dry compaction method. So that we'll see now the difference between these two. Okay, so in the paste method, which is a manual, it is frequently subject to human errors. So membranes may be defective. So one needs to have some practice on making these membranes. Then it will become some will gain expertise while prepare means in the membrane fabrication. Okay, so to gain expertise, you need to become familiar with this process by practicing. That means initially you may be your membranes may be defective when you start making, but while during once you practice making the membranes, you will gain expertise and you will be familiar with the process where is the issue. That means even spreading of the paste in the dye or in the mold is very important in preparation of the defect free membranes. Okay, paste method is easy, it is easy to use, but once you gain expertise, it will becomes very easy. You can make membranes without needing for the this hydraulic press. Hydraulic press and other kind of molds are required for applying dry compaction method. Okay, but it is time consuming, because a manual method it takes time for making the paste, then for spreading the paste into the dye or into the mold. It is then drying also it takes time. So overnight drying is also required. But in dry compaction method, we are not adding any water, so it will be powder form. It will be pressed in a hydraulic press. So it generally it does not require the atmospheric drying, but this paste method, in paste method, to prepare a consistent paste, we add water into it. Okay, we add water to the raw material mixture and then we make the paste. So it prior to sintering, some drying, some kind of drying like at ambient conditions, then drying in the furnace at 100 degrees centigrade, it is required for membranes prepared using paste casting method. Okay, so dry compaction method, it requires application of very high pressure, more than 50 megapascals. So it is used requires a hydraulic press to apply this much of high pressure. Okay, then when you compare the product that is a membrane prepared using same raw materials but with different methods. These two methods, porosity is lower than that of paste cast method, but in case of dry compaction method, porosity obtained was lower, whereas in case of paste method, porosity was higher. The main reason is we are adding water to make the paste. Then in the drying process, when the water evaporates, that also creates some vacant spaces within the membrane matrix. So that is adding to the porosity of the membrane. Porosity is the fractional void volume within the membrane matrix. So in case of the paste method, we mix and grind the raw materials. What are the raw materials here? Will be either main raw material is the either kaolin or fly ash. These are the low cost raw materials. So this raw material plus additives. Additives are required for making for creation of pores. So pore forming agent is added. Plus binder is added, okay, to keep the particles together. A binder is added, some like 5%, 5-8% of binder. Major it will be the 75% of the raw materials will be, major raw material is the kaolin or fly ash. So some 20%, 28% of pore forming agent is also added. Pore forming agent example is calcium carbonate. Okay, this calcium carbonate will decompose into CaO plus CO2. This release of this CO2 at the high temperature during the sintering process, it leads to formation of pores. So CO2 gas which is released will follow certain path to come out of this membrane. So this path created by the CO2 bubbles while they leave the membrane matrix create different pores. Okay, and binders like sodium metasilicate is used for making ceramic membranes because it forms silicate bonds among the raw material particles of kaolin or of fly ash. Okay, so then means we need to grind these materials. If grinding is fine enough, then we'll get uniform pores, because different particles of kaolin or different particles of fly ash will have different sizes. Okay, the size can range between 1 to 5 micrometers for the main raw materials. So fine grinding is useful in obtaining some fine pore size of the membranes. Okay, if the particles are, some are large, some are small, actually pores are created by the during sintering stage. These particles fuse together and create some gap or some void, which is later it becomes a pore. Okay, so if particle size is large, then the pore size is also large. So we have to reduce the particle size as much as possible. So grinding is also important. Grinding in the ball mill. So we mix the raw materials like these major raw material or principal raw material is kaolin or fly ash. Then some additives are used, pore forming agent like calcium carbonate or sodium carbonate or magnesium carbonate. So that can be used as pore forming agent. Nowadays people are also using some carbon materials as pore forming agents. Okay, then paste making with addition of water. So we add a small amount of water to make a thick and uniform paste, okay, to the raw material powder after grinding. Then this paste is casted over molds, because here we are making circular disc type membranes. So the mold also will be circular in shape. Then we have to spread the paste in the circular mold uniformly. Then we have to dry the membrane at 100 degrees centigrade. Then sintering of the membrane at a high temperature will result in the porous and rigid membrane. Okay, so this sintering generally requires high temperature. Okay, so in case of kaolin or fly ash, we are using low sintering temperatures. Even if we can also use high sintering temperature like 1200 degrees centigrade. If you use very high temperature sintering, then the resulting membrane also will have very high mechanical strength because of the mullite phase formed in the membrane. Okay, however, 900 degrees centigrade is sufficient enough to obtain the required mechanical strength of the membrane for about 40 megapascals. Okay, so this sintering temperature, 900 degrees sintering temperature, is sufficient enough to obtain a membranes with a high mechanical strength, that is about 40 megapascals. Then the prepared membranes are polished, then cleaned ultrasonically for further use. So this is a paste casting method. Another method is dry compaction method. So in this, we don't add water to make paste. We add only a binder, because previously here in the raw materials we are only using main raw material, that is the kaolin fly ash and pore forming agent. But in paste casting method we are adding some binder along with the raw materials. But here the binder is added after mixing and grinding of the raw materials, that is kaolin, fly ash and pore forming agent calcium carbonate or magnesium carbonate. Okay, then they are ground into fine powder. Then we add binder, and then that is PVA, polymer polyvinyl alcohol, as the binder for making ceramic membranes in using dry compaction method. Then this mixture is subjected to high pressure compaction, that is 50 megapascal or higher. Remaining all steps are same as that in the case of paste casting method. So difference is in these two steps. Now the materials that which we have chosen are fly ash and kaolin. So we used fly ash and kaolin as the main raw materials, that is 75% of the mixture, 75% of the mixture is either fly ash or kaolin. Then 28% is pore forming agent. Here we used calcium carbonate. Then 58% binder is used, that is sodium metasilicate is used as binder. Okay, so here these are selected main raw material. If you use fly ash alone, then we are getting large pores, more than 2 micron pore size, and low strength. Whereas if you use kaolin, then we have small pores and high strength. However, we want to find some application for kaolin in value added products like membrane. So we try to mix these two materials, fly ash and kaolin, in different proportions. Okay, because these two materials, fly ash also contains the silica and alumina similar to kaolin, but fly ash has high silica alumina ratio, that is a high content of silica as compared to kaolin. Now we prepared this 5 different sets of membranes, that is initially with fly ash alone, that is 75% fly ash and 25% additives. as we mentioned here, this 20% calcium carbonate and 5% sodium metasilicate, they are common in all these 5 sets of membranes. Only difference in these 5 sets of membranes is that the composition of 2 major raw materials, fly ash and kaolin, are varied. That means here it is, let's say out of 100 grams of the raw material mixture, 75 grams is fly ash and no kaolin is used. And in second case, 50 grams is fly ash and 25 grams is kaolin. Then in third case, 37.5 grams each, that is 50-50, or here it is like 1:0 and this is 2:1, here 1:1 and here 1:2. Okay, so from moving from M1 to M5, the fly ash content is decreasing and kaolin content is increasing. Okay, so we want to utilize fly ash so that we have to optimize the composition which contains fly ash. If we go for M5, that is made of kaolin only, then there is no fly ash used here. So this, we have to compare the properties of all these 4 membranes containing fly ash with that of the 5th one containing kaolin only. Okay, so method already discussed, the paste method, that means grinding in ball mill, grinding of the raw materials, then paste making with water, then casting in the circular mold, then curing under constant load. Because when we make cast the membrane manually and when we remove from the mold, it may get certain deformations. So we have to keep a uniform or constant load for certain period, like overnight 12 hours. Then the deformations will be settled or corrected. Then ambient drying for 12 hours. Then furnace drying and sintering. So furnace drying and sintering is employed in like this 3 steps. Like here 100 degrees centigrade drying in first step to remove the unbound moisture, then increasing the temperature slowly to 250 degrees centigrade and kept there for about 1 hour, so that the crystal water, that is bound moisture, will be released, and then the temperature is increased to final sintering temperature of 900 degrees centigrade. So here at this particular temperature, we are keeping the membrane for about 4 hours for completion of the sintering reaction. Okay. So once the membranes are sintered, then see, they are after sintering for 900 degrees centigrade, the furnace temperature is reduced slowly. That means heating is turned off after 4 hours. Then slow cooling or natural cooling to below 100 degrees centigrade. Then it is, the membranes are polished and cleaned ultrasonically. So they are then characterized using different methods. One is TGA, that is thermogravimetric analysis, is used for characterization of the raw material paste, not the sintered membrane. This is unsintered raw material paste is subjected to TGA to decide upon the sintering temperature and see the weight loss. Okay, that is change in the weight of the materials. So to decide upon the sintering temperature and observe whether the sintering process is complete or not. Okay, then the prepared membrane, that is sintered membrane, is subjected to same attempt to study the morphological characteristics, that is the homogeneity, surface homogeneity, and the pore size distribution and the shapes of the pores can be seen through the these micrographs, SEM images. Permeation test. This is most important characterization of the membrane, because through permeation test we can determine the average pore size, porosity, and permeability of the membrane. So these are the very important properties of the membrane that decide the final application, that is suitability of the membrane for a selected application. Then XRD is also done for the ceramic membrane to identify the mineral phases formed after sintering. Okay, during the sintering process, various phase transformations take place. So finally, if we study the XRD, then we can correlate the mechanical strength data with the phases identified on the membrane, in the membrane. Corrosion test is also done, because one of the advantage of the ceramic membrane is that their high chemical stability. So membranes are subjected to corrosion test by keeping them for a duration of 7 days in acidic and basic solution. So highly acidic solution and highly basic solution are prepared separately, and membrane dry weight is determined before and after 7 days of soaking period in each of the solutions. Okay, so these are the photographs of the membrane. The difference is that the M1 is fully fly ash, that is 75% fly ash, and M2 you have only the 50% fly ash and 25% kaolin. Then here you have 37.5% fly ash and 37.5% kaolin. That is 1:1 or 50-50 fly ash and kaolin. So here in M4 you have only 25% fly ash and remaining 58% kaolin. Okay, here in M5 0% fly ash. So when you use fully fly ash, the texture is some grayish texture is observed, and it with pure means with without any fly ash, with kaolin only, the membranes are means did not have any texture on it. They are white in color. Okay, this is only some for physical observation, and thermogravimetric analysis of these 5 sets of membranes is done. M1 is the fly ash based membrane, that is at the topmost line, and M5, which is the bottommost line, is a kaolin based membrane or kaolin based composition. Okay, so in between we have different amounts of fly ash and kaolin in the mixture. Okay, so if we as we observed, there are different weight loss patterns are there. Initially there is a high weight loss observed, especially with the M5 membrane. Then at one stage, that is here, there is another weight loss. So we'll see what is the meaning of these weight losses. Initial weight loss is because of the unbound moisture or free moisture, because we are making the membranes using paste casting method. So we are adding some water for making the paste. So that free moisture evaporates at around or at below 100 degrees centigrade. So this here it corresponds to below 100 degrees centigrade. That is up to 100 degrees centigrade, the free moisture evaporates. And the difference between the fly ash and kaolin based membrane is that actually in the preparation, the fly ash based membrane required less amount of water for even with less quantity of water, we are able to prepare a consistent paste. But with kaolin, which absorbs some water, it required high amount of water in making the paste, in the formation of paste. Therefore, correspondingly, high weight loss is observed for M5 membrane that contains high amount of kaolin. Okay, so this is only free moisture evaporation. Then coming to the phase transformation, which is one of the important step in the sintering, that is phase transformation of kaolin to metakaolin, that occurs at temperature in the temperature range of 400 to 600 degrees centigrade. So kaolin to metakaolin, it produces means it helps in it imparts mechanical strength to the membrane. Okay, so kaolinite phase is transformed into metakaolinite with the removal of this hydroxyl group, okay, in the form of H2O. So when this is the important step in the sintering, that is conversion of kaolinite to metakaolinite, that helps in imparting the mechanical strength to the membrane. Okay, so up to 1000 degrees centigrade, no other major transformation is noticed, but here between 600 degrees to 800 degrees centigrade, there is another step is observed, that is weight loss, major weight loss. That is because of the decomposition of the pore forming agent CaCO3, calcium carbonate. So calcium carbonate decomposes into CaO and CO2. So this release of CO2 bubbles or gas bubbles in the during the sintering are due to the decomposition of calcium carbonate, that is the pore forming agent, imparts porous structure to the membrane matrix. Okay, so one phase transformation, that is around 400 to 600 degrees centigrade, in this interval is imparting the mechanical, that imparting the it is responsible for mechanical strength of the membrane. And second weight loss here, that is the decomposition of the pore forming agent is responsible for porous structure of the membranes. Okay, and these are the same micrographs of the prepared membranes M1, M2, M3, M4, M5. So when you observe the closely all these images and compare, we notice that the size of these pores on the surface are getting smaller and smaller as we increase the kaolin content in the mixture of the raw materials. So this is not membrane same, it is for one solute which we used humic acid. So we'll discuss about that later. So first we now focus on the images of the membranes, that is 5 different membranes, M1, M2, M3, M4 and M5. Okay, so when we compare the surface of these membranes, the pore size is getting smaller as we increase the kaolin content in the raw material mixture. Okay, so next characterization is the water permeation. So here we have one is the air we can use air compressor or nitrogen cylinder, gas cylinder can be connected to pressurize the permeation cell. Okay, then this membrane is fixed in the bottom compartment of the permeation cell, and cell is loaded with water, then it is pressurized with the help of a compressor, so that we'll get the permeate. Okay, so permeate flow rate is also measured, and the permeate flow rate at a given pressure will be noted for different pressures. So the permeate flow rate versus the pressures will give us the some of the properties of the membrane, that is permeability and the pore size. We'll see how these are related. Okay, so this is the close-up of the permeation cell. So this bottom compartment is fixed with the membrane. So membrane is fixed in the bottom compartment. Then a cell is mounted, and this cell is filled with the feed, and it is pressurized with the help of any nitrogen gas. Suppose if we are doing the gas permeation, then we should use only a single gas like nitrogen gas. Okay, when we are performing liquid permeation or water permeation, we don't require any gas, but to maintain the pressure or to pressurize the cell, we can connect it to a compressor, okay, air compressor. Then at various pressures, that is transmembrane pressures, we measure the flow rate of the permeate, and then they are related by means of modified Hagen-Poiseuille equation. This is a modified Hagen-Poiseuille equation. In this, we assume that there are n number of pores per unit area of the membrane, and all pores are cylindrical and of same dimensions. Okay, so if we consider only like a single pore, then delta P is related as 8 mu L into Q, that is volumetric flow rate, divided by pi r power 4. Whereas this Q is volumetric flow rate. So when you rearrange the terms, you will get Q is equal to pi r power 4 delta P divided by 8 mu L. So this is coming from the Hagen-Poiseuille equation for a single pore or single cylindrical pore with constant cross section. Now we are having n number of pores. Okay, so total flow rate through all the pores is equal to n pi r power 4. N is the number of pores per unit area. So here also you will get flow rate per unit area of the membrane. So number of pores per unit area is also known as pore density. Okay, so here the main assumption is that all pores are of same size, okay, and they are cylindrical, straight cylindrical. So Q by A, volumetric flow rate divided by membrane area, is the flux, permeate flux. Okay, here it is pure water flux. We are because we are using only pure water for studying the characteristics of the membrane. So this is related, means the pore size and the flux to the membrane at a given pressure difference are related. Now we have means this n phi r square is replaced by epsilon, which is the porosity. Porosity is the total volume of all pores divided by volume of the membrane. Okay, so this n here is number of pores by area of the membrane into pi r square. Okay, now this pi r square, if you multiply numerator and denominator by L, so n is number of pores into pi r square is the cross-sectional area of the pore opening, each pore opening, this area multiplied by this length will give you volume of each pore. Pi r square L is the volume of one pore multiplied by number of pores, capital N. Because this N is pore density, number of pores divided by cross-sectional area. Okay, so you are multiplying by the pore length, the numerator and denominator. This, so pi r square L is volume of one pore into N number of pores is the total volume of pores, that is pore volume of the membrane, divided by cross-sectional area of the membrane into L is the pore length, which is also equal to thickness of the membrane. Because here we are assuming that membranes has pore cylindrical, straight cylindrical pores. So the length of the pore is equal to thickness of the membrane. So membrane thickness into membrane area is volume of membrane, that is total volume. So pore volume divided by total volume is nothing but the porosity. So n pi r square is replaced by epsilon, which is porosity of the membrane. And here you have n pi r power 4. So r square is left, that is epsilon r square delta P by 8 mu L. So all these terms are grouped together and it is written as LH, which is hydraulic permeability. Permeability or hydraulic permeability into delta P. Now we are determining the flux, that is pure water flux through the membrane at different pressures. 1, 2, 3, 4, 5. So at different pressures, we are determining the pure water flux through the membrane. Okay. So for M1 membrane, the data is plotted and fitted to a straight line. So slope of this straight line, that is slope of the line fitted between the flux J and delta P, that is the driving force J and delta P. Here the final expression is JW is equal to LH delta P or Y is equal to MX. So M here is the slope. All these data lines pass through the origin and the slope represents the LH value or permeability of the membrane. Okay, so when we plot the flux, permeate flux or pure water flux, this is the pure water flux, not the permeate flux. Okay, so pure water flux against the transmembrane pressure delta P and fit a straight line, will get the permeability of the membrane as represented, that is represented by the slope of this line. Okay, so slope of this line represents permeability LH. Once we get the permeability, we can relate it to LH is equal to epsilon r square by 8 mu L. Mu is viscosity of water, L is the thickness of membrane, this is known, and this is porosity is determined separately, and LH is known by the are known from the slope of these lines. Okay, so now we can determine R value. R is the pore radius. Okay, so average pore radius can be found from the relation. So pore diameter is twice the pore radius, that is dP is equal to 2R, that is 2 times this. Okay, then pore diameter is calculated from this slope of this line, each line. So we'll get these pore diameters for different membranes, that is M1, M2, M3, M4, M5. Okay, as we are increasing the kaolin content in the membrane from M1 to M5, the pore size is decreasing and porosity is increasing. Now we'll see porosity increased with increasing the kaolin content. We can see TGA. That means in TGA, we observed that there is a highest amount of total weight loss. That is total weight loss. That is starting from 100 to this value. That is approximately 65. The difference is 35 weight %. So this much of weight loss is observed in case of M5 membrane. Okay, so this the weight loss is also it corresponds to a high amount of porosity. Okay, so porosity is increasing with kaolin content. It is correlated with TGA observation. The weight loss, highest weight loss in the observed in TGA for M5 membrane also corresponded to a similar increase in the porosity of the membrane. Now we have the data of pore size and porosity. Then membrane also is subjected to X-ray diffraction, that is M1, M2, M3, M4, M5. So these different membranes have different compositions, and these compositions means with increasing the amount of kaolin, there are differences in the amounts of various minerals, especially with M1, M2, that is a high amount of fly ash. We have nacrite and dicite in high amounts, whereas with kaolin we observe that metakaolinite amount is very high. Okay, So now when we see the hardness values of these minerals observed from the XRD, the hardness values are different for different minerals, and anardite is common in all the membranes, and this nacrite and dicite, that is this one, and nacrite is this. So they are mainly observed in case of the fly ash based membranes. Okay, so these have low hardness and also corresponded to low strength of the membrane. So M1, M2, as we increase the kaolin content, the strength is increasing. So mechanical strength increased with increasing the amount of kaolin. This is due to formation of metakaolinite and quartz in case of the kaolin based membranes. But in case of the fly ash based membranes, that is the first two, this M1, M2, we did not means they corresponded to low strength, mainly because of the low hardness minerals formed nacrite and dicite. Okay, so this then the chemical stability analysis is done, and we can see that there is a weight loss. Weight loss is significant in case of the membranes kept in HCl, that is acidic solution. Okay, so high amount of weight loss is observed for the fly ash based membrane, that is M1, M2. So this is mainly because of the nacrite and dicite, which are formed in during in the sintering process for fly ash based membranes observed in the XRD. So these nacrite and dicite phases are generally unstable in acidic conditions, and hence the weight loss is high amount of weight loss is noticed for fly ash based membranes in the acidic solutions. The weight loss, it should be less than 5%. That is, if it is even below 5% or 4%, then they are preferable. Okay, but in case of basic solutions, they are found, all membranes are found stable. And when we compare the properties of all membranes, the pore size is decreasing with increasing the kaolin content, and pore size is small for these last two membranes, that is less than 1 micron. Porosity is high for M4, M5 membranes. Mechanical strength is also high. Chemical stability is also good. That means weight loss is low. Low weight loss corresponds to good chemical stability. Therefore, these M1 and this M4 and M5, they are equally good in terms of all these characteristic properties. Okay, but which one to use for applications? We'll see. If we our objective in the beginning is to utilize fly ash in value added product, that is membrane. So we choose M4 membrane because it is relatively less expensive, and as it contains 25% fly ash. Therefore, M4 was chosen as the best low cost membrane for further use in the microfiltration applications. Okay, so M4 is chosen based on all these characteristics which are close to M5, that is kaolin based membrane. Okay, it contains 25% fly ash and 58% kaolin. Now coming to the applications, we use this membrane for two different applications. One is the separation of humic acid. Humic substances are also used in fertilizers due to their water holding capacity, and they have complex chemical structure, and they are chemically reactive because they contain these functional groups COOH, C11OH. They can interact with red blood cells. Okay, but it is also found in surface water up to concentrations of 50 mg per liter. However, the permissible limit in drinking water is only 2 mg per liter. That means this amount of humic acid is not safe for drinking, hence it is to be removed from drinking water. So presence of humic acid in water is undesirable. A few reasons is because it affects the taste and odor and color also of the water. It leads to secondary pollutant, that is with the formation of highly toxic and carcinogenic trihalomethanes during chlorination or disinfection process. Because drinking water is subjected to various treatment process in the municipal water treatment plants, then finally subjected to chlorination or disinfection. If these humic acids are present in the water, they produce a secondary pollutants which are highly toxic and carcinogenic. Therefore, we have to remove humic acid from water. In surface waters, the concentration is found up to 50 mg per liter. Therefore, synthetic solution of humic acid is prepared with the same concentration 50 mg per liter, and it is filtered using our membrane M4. Okay, so concentration of humic acid is estimated using UV visual spectrophotometer at a lambda max corresponding to 254 nanometers. Okay, now the humic acid particles, because it is as we have seen in the semi image, the last one is the semi image of humic acid. Humic acid is exists as particles in flaky particles, that is like pieces of paper. Okay, they are not spherical, they are not cubic, but they exist as flaky particles. So this particle size ranges between 5 to 10 micron. For majority of the particles have this size, so they can be easily separated using our microfiltration membrane. As we have seen, the pore size is less than 1 micron for the both M4 and M5 membranes. Therefore, the separation result is shown here. It is the permeate flux against the time. So the permeate flux decreased with the time. Actually, this is different from pure water flux. Pure water flux is constant at a constant pressure, but here at a constant pressure, permeate flux decreasing with time. It is not constant, but it is decreasing with time. Okay, so this decrease is because of the membrane fouling. Initially, when we used water permeation, there we do not have any impurities or any solutes to block the pores, but here we have solute, that is humic acid particles. They are blocking the pores, and they are means causing fouling to the membrane due to the formation of cake layer. And after 20 minutes of use, that means although we used it for 1 minute, but the data is analyzed up to 20 minutes, then membrane is regenerated by cleaning and backflushing. Okay, so then we checked that the initial flux is recovered. Almost 92% of the initial flux was recovered by cleaning and backflushing. So that is one advantage of flat type ceramic membranes compared to the tubular membranes. That means we can recover the initial flux, that is by regenerating the membrane. Regeneration of membrane is easy in case of flat type membranes as compared to tubular membranes. So now this decline in the flux, flux is decreasing because of fouling, but we have to understand what is the fouling mechanism. So there are various fouling models, flux decline models. These 4 are very popular. Intermediate pore blocking model, that assumes that pores like membrane is having pores. So these pores are blocked partially by the these solute particles, and hence effectively the pore size decreases. That causes reduction in the permeate flux. So means if the data yields a fit to the means J inverse versus time gives a straight line, then we can our assumption that this assumption, that is pores are partially blocked by the solute particles, will be correct. Similarly, complete pore blocking model. In this model, some of the pores are completely blocked by the solute particles, whereas others are unaffected. And in standard pore blocking model, the particles are smaller than pores and they enter into the pores of the membrane, and they cause blockage to the flow of the solvent. And in the final one, cake filtration model, these particles are accumulated on the surface of the membrane, and cake layer is formed. Cake layer is, it is the layer, concentrated layer of the solute particles. So our data is fitting well with the relation for cake filtration model. Therefore, we concluded that the membrane fouling is because of cake formation. Okay. Also, amount of humic acid rejected by the membrane is very high, especially at low pressure. If you apply very high pressure, that is 2 bar of delta P, the rejection is less, because high pressure is the driving force for transport of the solvent, and in this case the particles of humic acid are flaky in nature. Suppose if you want to throw a paper out of a small window, what we do, we fold it. Similarly, at high pressure, that also causes the deformation or folding of the particles in the solution. So high pressure resulted in less rejection. That means only, let's say 95% average, on an average 95% is rejected. So 5% is passing to the pores. Okay. But in case of 1 bar pressure, 1 atmosphere pressure, more than on an average about 99% of the particles are rejected by the membrane. Only 1% are passing to the membrane. So at 1 bar pressure, the average concentration in the permeate was only 0.77 ppm, whereas 2 ppm is permissible. Therefore, we achieved the desired separation of humic acid at 1 bar pressure using a membrane M4. Similarly, we used the same membrane for oil water separation of oil water emulsions. Mainly, these main source for oil water emulsions is the wastewater generated from oil wells and petroleum refineries. So generally, they come at very high concentrations. If the concentration is very high, more than 1000 ppm, then they can be separated easily by gravity or other skimming process. Okay. However, after this stage of gravity separation and skimming, still there will be some oil left in the water, that is at low concentration. Under low concentrations, the solution is very stable. That is, stable suspension of or stable emulsions are formed, and they are not easy to separate by gravity or skimming methods. Okay, they require use of membrane separation. So safe discharge limit for oil in water emulsions is 10 mg per liter. However, it is about 1000 mg per liter can be easily separated, whereas less than 250 mg per liter is difficult to separate by common processes. So we used membrane separation for two concentrations, 100 mg per liter and 200 mg per liter solutions. Okay, so these oil in water emulsions are also analyzed for droplet size, and it is found that average droplet size is that means at low concentration the droplets are smaller in size. At high concentration, droplets are bigger in size. So bigger droplets can easily float on water, means that they can with the time, if you allow sufficient time in the settling tanks, then this due to gravity low density, the water this oil droplets float and they form oil layer on the surface, and they can be removed by skimmers. But these means low concentration emulsions, they form stable suspensions, so they require separation by membrane. So we used membrane separation and UV visual spectrophotometry for determining the oil concentration in the emulsions. So at 100 mg per liter oil concentration, the removal is satisfactory, and at 200 mg per liter also low pressure is giving low flux, high pressure gives high flux, because uh, the pressure is the driving force for transport. So flux will be obviously higher, that is proportional to the delta P, that is pressure. However, our interest is on rejection, that is separation efficiency. So rejection is high for low pressure, rejection is less for high pressure. Okay. So why rejection is less for high pressure? As we discussed in the previous case, same applies here. The droplets are not solid particles, they are fluid droplets, so they can deform, even they can pass through small pore. When we apply high pressure, this shape deforms and it can pass through the smaller pores. Therefore high pressure is always means in this particular case of oil water emulsions, high pressure is giving low rejection. So when we analyze this flux decline, that is flux decline for permeate flux decline by various models, here also it is the result is saying that the reason behind the weight loss, or reason behind the decline in the flux or fouling, is due to cake layer formation. Okay, so this is observed, same is observed at 200 mg per liter oil concentration. So this is about the future work. Actually, what we did is utilized fly ash. At least in one of the membranes, we have successfully applied. We utilized 25% fly ash and 50% kaolin. So, and those membranes have good characteristics that are suitable for microfiltration applications. Even to enhance the process from microfiltration to ultrafiltration, we need to make composite membranes. So our future work will be on preparation of composite membranes, and some references are shown here. And thank you all for your patience, and thank you for the organizer. I thank the organizers for giving me this opportunity.
Thank you, sir.
Thank you, sir.
Sir, after a long time, we'll meet. So, thank you for your nice presentation.
Thank you, ma'am.
Okay, sir. Any questions from our participants? You can, all the participants, it is a request that you can also ask your questions to direct to the speaker. So thank you, sir. Thank you for your accepting our invitation, and you are giving your valuable time for enlightening the knowledge to the participants as well as for us also. Thank you once again, sir.
So, welcome, ma'am.
Rudra sir, anything
Yes.
else or we can?
No, any doubts from any audience?
I think there is in the chat box. It is not in chat box also. The participant can can give your questions so that sir can answer all these questions. In chat box, you can also have it.
So I don't think so any doubts is there. So thank you very much, sir. It's a kind presentation and good presentation. Thank you, sir.
Okay, thank you. So shall I leave now?
Yes, sir. Yes, sir. You can.
Okay, thank you very much.
So next session will start at 1:30 p.m. So everybody should join in that lecture. That is the 11th lecture in the FDP. 3 more lecture is there. Okay. Thank you very much. Sir, Anup sir. Anup
Yes,
sir.
sir. Yes, sir. Tell me, sir.
Name is Bibak Kumar Bansal. Bansal.
Okay.
Timing also change, sir. Oh, timing ठीक है. Okay.